Okay, this is section 2.5, which we're going to talk about how to evaluate limits algebraically. So we talked about how to do it at the table, how to do it graphically, and we also talked about if the function is continuous at the point that you're taking the limit, that we don't have anything to do because the value of the limit is the value of the function. So the first sort of question that you may then ask is, when can and can't I evaluate a limit? By just plugging in the relevant value of x and being done, right? So when is the function value the same as the limit value? And hopefully, if you were paying attention in class on Wednesday, you know that that value, or that happens when your function is continuous at that point. And the big times that you can't is when you get what's known as an indeterminate form. So, what is an indeterminate form? So we've actually already talked about one of them, and I think we saw some examples the other day. The idea of 0 over 0. It's an indeterminate form because we really don't know what that is, right? Some people in this class could argue that it's 0 because there's a 0 on top. Some of you might argue that it's 1 because it's 0 over 0 and anything divided by itself is 1. And some of you might argue that it doesn't exist because there's a 0 in the denominator. And in fact, none of those things are true. When we get this, it just means that we need to do more work to really decide what it is. So 0 over 0 is not anything. It doesn't mean anything. So we have to do more work to find out what it does mean. Another one is infinity over infinity. So here, again, someone could argue that it's infinity because it's getting really big on top. Someone could argue that it's 0 because it's getting really big on the bottom. Someone could argue that it's 1 because it's a big number divided by a big number, that's 1. So because we can't really say what it is for sure, we have to do more work to find out what the real value of something like that is. And the last one that we'll kind of focus on in these sections, there are more, but these are the three that we'll kind of focus on for now, is infinity minus infinity. And that's another one that's really questionable. Because what if, you might say it's 0, right? Infinity minus infinity is 0. Or you could say it's a negative number, right? Because what if the second number is larger than the first number? Or you could say that it's a positive number because the first number is bigger than the second number. Again, it's something we can't give a specific value to, so we call it an indeterminate form. And anytime you get one of those, you have to really do more work. And the question is, what kind of work can you do? So if the substitution method works, that's when the function is continuous at that point, you're done. You know what the limit is. But other times, and these particular times that you get indeterminate forms, you want to use some sort of algebraic manipulation. So that's like factoring, rationalizing the denominator or the numerator, etc. So we're going to look at some examples of doing those particular algebraic techniques. So the first example is this one here. The limit as x approaches 2 of x squared minus 4 over x minus 2. And generally what I do with limit problems is I always try to plug it in first, because if it's continuous at that point, I'm done. I don't have to do any of this crazy stuff. So I'm just going to try it out. I never set it equal because if it's one of these indeterminate forms, I don't want to have an equal sign with something that's not a number. So I just kind of go over here to the top and I plug this stuff in. I get 2 squared minus 4 over 2 minus 2. So I am going to get 0 over 0. So that tells me that that doesn't work, and I need to try something else. Be very careful here. This notation is really important, and hopefully in the motivating example we saw from a couple sections ago, you remember that you've got to have a limit here. You can't just write equals. So if there's a limit here, you better have a limit here until you actually take the limit. So a way to simplify this, so the idea is that the substitution method didn't work, so now we're going to use some form of algebraic manipulation. And here, if you notice, the top factors really easily as x minus 2 times x plus 2 divided by x minus 2. And so then we can cancel those because there's a limit sign here, right? The limit we can always do algebraic manipulation with. We could not do that if the limit sign wasn't there. So the limit as x approaches 2, all we have left is x plus 2. And if we plug in 2 now, you get a number, and that's your limit. So we get 4 for the limit as x approaches 2 for this limit. So the key thing here is that you can do the algebraic manipulation, you can simplify because you have the limit sign in front. And the limit is equal to the original function, even if you simplify. But that's why if you take the limit signs, remember from the example, if we took the limits out, those two things would not be equal. But the limits are, and that will be true as we move forward. So keeping that notation there is really important. I know it's painful to have to write that every time, but you keep writing it until you actually plug in and take the limit. So we can do a similar example over here. Again, I'm going to come up here at top and just plug in the numbers and see if I can get my answer to work out. If I plug everything in, it looks like I get negative 8 over negative 2, which is 4. And that's an answer, that's a number, so I'm done. So the answer here is just 4. So the key thing here on this example is we got a number. So don't do the algebraic manipulation if substitution works. Okay, because that could actually end up giving you the wrong answer. You could simplify out so much that you actually get the incorrect answer. So be really careful about doing algebraic manipulation on things where the value of the function is the limit, because the function is continuous at that point. So the function's continuous at 0, so you don't have to plug anything, you don't have to check anything. This is equal to 4 just by straight definition, straight plugging it in. Okay, I'm going to look at a lot more examples. Here comes another one. This is x cubed minus 8 over x minus 2. So again here, another thing you can do is recognize that this function is certainly continuous at 3, because if I plug in 3, I'm going to get a number back. So you can immediately write the equal signs, because you're going to plug in the 3. 3 cubed minus 8 over 3 minus 2. And if we simplify that out, that's 27 minus 8 over 1, which I believe is 19. So that's a pretty straightforward one. So again, don't do the manipulation, don't do the simplification unless you know for sure that you have something that is an indeterminate form. So for example, here on this one, on letter D, if we plug in 2, we do get 8 minus 8 over 2 minus 2, 0 over 0. So that's no good. So that's definitely not good. So we want to rewrite this. Limit as x approaches 2. On top, we can factor that. Remember, that's a difference of cubes. So that's x minus 2, x squared plus 2x, and then plus 4, I believe, is the correct way to factor that. And that's still divided by x minus 2. Because the limit signs are here, we can cancel these and rewrite this as the limit as x approaches 2 of x squared plus 2x plus 4. And we can just plug in 2 now because there's no funny business going on. We get 4 plus 4 plus 4, which is 12. So that's our answer for that one there. Okay, so the first couple that I did were about factoring. And anytime you can factor, that's going to be a great thing to do. The next one is something else that's also kind of interesting. It's a little bit different in terms of an algebraic manipulation. So up here on top, you'll see the limit as x approaches 1 of x plus 3, square root of x plus 3 minus 2 over x minus 1. And if I come over here and just kind of try to plug stuff in, I get that goes to square root of 4 minus 2 over 0, which is 0 over 0, so that's no good, right? So we don't want to do that. Scratch that out. Don't let anybody know that you did that. That was your sort of test. So now what we'll do is figure out a way to make this look prettier. And there's obviously not an easy way to factor this, but hopefully you remember that square root is the thing here that's really causing you troubles, and you can always get rid of a square root by multiplying by its conjugate. So hopefully you remember that idea. So I'm going to multiply this by x squared of x plus 3 instead of minus 2. I'm going to go plus 2. That's the opposite. And if I do that to the top of this equation, in order to keep it an equivalent expression, I'm going to multiply also the bottom by that same conjugate, because that's like multiplying by 1, right? This is this over this. Otherwise, this isn't going to make any sense. If I just multiply the top by that, then I'm doing a completely different problem. So I need them to be equivalent in terms of where the limit is at x approaches 1, and so whatever I do to the top, I should do to the bottom. And now, once you do that, when you go to FOIL this, right, you FOIL this times this, this times this, this times this, and this times this. Hopefully you recognize it as a perfect square. It's a factoring of a difference of squares. So really, on top, you end up with something really nice. You just end up with x plus 3 minus 4. So the first term squared minus the second term squared. And if you need to FOIL it all out and see that, that's fine. You'll get the two terms in the middle will cancel. And then on the bottom you have an x minus 1 and then square root of x plus 3 plus 2. And I would not FOIL all that out. The only thing I would ever FOIL out is the conjugate stuff to simplify that part, because if you do that, then you'll see that you get the limit as x approaches 1 of x minus 1 on top and x minus 1 on the bottom, square root of x plus 3 plus 2. And the beautiful thing about this, hopefully you recognize, is that these things cancel. And so we take the limit as x approaches 1. Be careful, there's a 1 on top, because this is still in the denominator. And now we just plug in 1, and we're going to have a nice answer, square root of 4 plus 2 in the denominator. So that gives us 1 over 4, if you're careful in the simplification there. So this is another really great example of something we do a lot. Factoring is one, the second is multiplying by conjugates. I have one more example I want to show you today, and that'll give you some of the basic ideas behind evaluating limits algebraically. We'll do some examples in class and finish the notes for this section, which I think there's a couple more problems. We'll do all of that on Monday. Okay, one final example, something a little bit different. This is letter F in our example from our notes. The limit is x approaches 0 from the right, remember, of 1 over x minus 1 over absolute value of x. And if you were to plug this in, if you think about this just in your head and thinking about what this would do, 1 over 0, as x gets really close to 0 from the right, so you think about plugging in like 1 over 0.1, 1 over 0.01, 1 over 0.001. What are those numbers doing? Hopefully, if you're recognizing it, you're plugging in really small numbers close to 0 and dividing by them. So you're really getting huge numbers here. Oops. So this is going to be going to infinity. And similarly, here, right, you're plugging in really small numbers, really tiny numbers in the denominator, dividing, taking absolute value, which they're positive anyway, so it doesn't matter, you're getting infinity. So you get infinity minus infinity when you just first think about it. And that, we don't know what that is. So we need to redo some work. So we can rewrite this, and in this case, it's about thinking about how to rewrite the absolute value. So this is 1 over x, 1 over the absolute value of x. Now normally that has two different sort of ideas, right? If you're coming from the right, it's one thing, and if you're coming from the left, it's another thing. But here we're coming from the right, correct? So if we're coming from the right, 1 over the absolute value of x, as we come from the right, is the same as 1 over x. Those things are no different as you come from the right, because the absolute value signs don't matter, because the numbers are already positive. So we can convert that to this inside of the limit because we're coming from the right. Otherwise, these two things are not equal. But because we're taking time at the limit and just what it's getting close to, the things that this gets close to as we come from the right are the same as what this gets close to. So we can make that algebraic change to help us solve this problem, because now we just are left with 0. 1 over x minus 1 over x is 0. X approaches 0, we get 0. So that's just kind of a slightly different kind of problem to think about how you would change absolute values as you get close to certain things. So like I said, we'll work a few more questions. There's a back page to the notes for section 2.5 and one more other question there that's a little bit a subtle difference. And then after that, we will work some problems in class.